Understanding the derivative and integral. Example, an automobile accelerating. During the car's acceleration, the velocity would represent the first derivative. Derivatives are essentially rates of change or slopes, y over x, and in this case the first derivative represents the velocity of the car, or its distance divided by time. If we were to get the derivative of the first derivative, we would then reach the second derivative, which would be the acceleration, or the distance divided by time, then divided into time once again. If we go backwards from the first rate of change, slope, first derivative, or the distance over the time, this would lead us to the original function, which represents the area under the curve, and in this case it would be the distance attained by the car during its acceleration. Under the curve, the y multiplied times x. So if you're starting out in calculus, you probably are familiar now with the power rule. And for instance, if you were to get the derivative of x cubed, it would require the exponent to be reduced by 1 and then placed as the coefficient times the base. So x cubed would be differentiated into 3x squared. If we get the reverse of this process, then we have the integral. So in this case, here's an indefinite integral, and we are reversing the process. So if we had 3x squared and we were to find the integral, the integrand of 3x squared, it would come back into 3 or x cubed. And in this case, since it is an indefinite integral, we'd have to add it to some constant. So here we increase our power by 1, keep our base, x cubed, x squared becomes x cubed, and then when we test it and the exponent comes down, it has to cancel out with some value, so 1/3, and then we have x cubed plus c. So a better way to explain it is a practical example. So if we focus just on the red text and the red curve, we can see that the speed observation during acceleration was witnessed at every second, and then we plotted these points. We noticed that the acceleration is not linear and it behaves as a quadratic function. So using the vertex rules, or the vertex method of creating an equation from a quadratic curve, we then get this function for which, when the second time is placed or substituted for x, we can calculate the velocity at each given point in time between 0 and 6 seconds. So therefore, the equation which describes the acceleration curve behaves as the first derivative, or y prime, because it's a velocity output. So therefore, the area under this curve, the red curve, would represent the total distance attained during the acceleration. Now if we focus on the green part, if we were to calculate the average acceleration on a linear method and then solve for the total change in distance using 1/2 at squared, you would come up with the wrong answer of just 263.88 feet distance attained during the acceleration, or it would be this line, take it from y is equal to mx plus b linear equation, and the distance that is nonlinear will be excluded. So this will actually be wrong. So what we have to do is now focus on the blue part here. So we use the integrals power rule. We find the definite integral using the power rule for integrals. So we put this equation in here in blue, and then we integrate each component of the equation. It's a quadratic equation, so we get the following here. And then we have to take it over the time limits of 6 and 0. So when we substitute the 6 for x, and then we subtract it from substituting 0, if we put 0 into all of these, it comes out to 0. So the actual distance will be this expression here, and it comes to 352.32 feet distance during this given acceleration, because now we're accounting for the nonlinear distance attained, as well as the if this was like a final speed of 88 feet per second, initial at 0, and then time is 6 seconds, we are actually calculating based on the correct function. It's a quadratic function, not a linear one. So you then can use the rules for integration to calculate the area under the red curve. I just put the green part here to make a point that if you did not have a speed observation every second, so you could draw or plot a graph, you would then end up with the wrong distance traveled. It would not be a generic linear acceleration. So actually the amount of distance is unknown until you do the plot analysis to find out what kind of a function or graph you are dealing with. So then if we go back to the original function here, I'm sorry, the y prime, this is the original function from the acceleration. So, but it does behave as a first derivative. So I had to be a little careful saying original function, but this would be the equation for the plotted points of the acceleration. So if we go to the quadratic function describing the graph of the acceleration, it is the first derivative. So we must then find the derivative of the first derivative to get the second derivative. So again, we apply the rules for the power rule in differentiation. 2 comes down times the coefficient to the x to the 1 power, and then 29.28. The x is out, and then the constant is 0. So we did that right here. So the second derivative, the acceleration function, negative 4.88x plus 29.28, where x is greater than 0. We cannot include 0 in the x metric because the acceleration starts at the end of 0. So it's 1 to 6, not 0 to 6. So when we go ahead and substitute the time limits from 1 second to 6 seconds for x, we then get a vastly different acceleration per each given point in time. So the first second, 24.4 feet per second squared, second, 19.52 feet per second squared, and on and on. So you can see that when we come to the end of the 6 second, or we come to the 6 second, our acceleration comes down into 0, which proves that the metric or the derivation is correct. So we can kind of intuitively look at the graph and see that we have a spike in acceleration, and then it starts to taper down and come to 0. And our time limits are between, technically on acceleration, 1 to 6, and velocity 0 to 6. So the functions, or the ability to figure out the rates of change at any given point in time, are what the derivative and integral represent. And it's actually very fascinating that all the different rates of change on not just 2 axes but 3 axes can be ascertained using the derivative and integral. Case in point, if you were dealing with, let's say, electrons per second through a wire, the voltage, you could also figure out the electrons per second squared if you were dealing with a change in voltage, and then you can reverse the first derivative into the integral to calculate the number of electrons. Other applications, dollars earned per month, that would be first derivative, that would be like the velocity function, and then dollars earned per month squared, that would be the increase or decrease of change in the amount of dollars earned per month. And then if you take that first derivative and reverse it, you could calculate the total dollars per month, especially with a nonlinear rate of change with respect to the amount of dollars earned per month. So from financial applications to electrical to anything that has a rate of change, cells and molecules, anything under the sun you can think of that has a rate of change, you have ability to figure out what the rate of change is at a given point in time. So it is in reference to the infinite and the infinitesimal, from the smallest to the largest. So the point to make is that there are many rules of differentiation and integration that you may pick up along the way in your calculus series training and experience. And then there's a lot of other applications that can be solved that bring forth a problem-solving economy and or ability to help and solve problems in general. So this is the basic explanation of the derivative and integral in calculus. Thank you for watching this video and have a great day.